Somebody said single pole, single throw. Yeah, they're all single pole, single throw. Okay, so here's one way to solve it. Turn on S1. Wait, somebody's got a, oh, close. Turn on S1 and wait 5 minutes. Then turn off S1, turn on S2. Go into the room. The bulb that's lit has to be connected to S2 because you just turned on S2. The bulb that's warm has to be S1 that you just turned off. And the bulb that's cold has to be S3. We don't know without knowing which bulb is warm and cold without which is lamp A, lamp B, lamp C. But that's one way to do it. There's other ways you can turn on 2, turn off 1, and pretty much do the same thing, but this will do it. Okay. Everybody follow that?
No.
Thinking outside the box a little bit. Okay, before we forget, and I am recording, by the way, somebody is going to ask me. I actually remembered. Exam 1 is Thursday, this Thursday, the 22nd. Is going to be Thursday, the 22nd, during the lab period. Professor Atwood's going to proctor the exam. So we'll have a regular class, and then Thursday afternoon is when you'll do the exam. I'm not going to do a review session because we have too much material to get through during class, but if you want, we could set up a review session on Wednesday afternoon, evening, whatever, that fits a mutually convenient time.
Is it going to be online or we have to go to?
No, there's what? Which, the review?
No, the exam.
The exam will be during the lab period in the lab, in person.
Okay.
I don't know about
I don't
anybody.
know what room. I don't know what room you're in, whether it's 108, 110, 112, but it's somewhere in cluster D. Whatever room you normally go to for Professor Atwood's class is where you go for the exam. Natasha, you had a question?
Sorry, I was just gonna say that I don't know about anybody else, but like for me personally, the only time that I could do Wednesday would be either in the morning before work or in the evening after work, and I get out of work at like 9. Like I would be available at 9, but I don't know if that's like way too late for you guys.
All right, what I'll do is, I'll do a survey in Google like we do with the quizzes, except it'll be a survey, and whatever time fits the most number of people is when we'll do the review session. It'll also be a matter of, I'll ask on the survey if you're interested in a review session, because obviously if you're not interested in a review session, then I'm not going to worry about what time you're available or not available, and skew all the results for everybody else. But I'll do that as soon as we get done with class today. I'll send out a thing, and then I'll send out an email once I've gotten the results from everybody about their availability.
Okay, thank you.
Okay. Um, okay, let me go back to when we left off. All right, when we left off, we had gone through some series circuit problems. We figured out that, and we figured this out a couple of classes ago, that whatever the voltage is across the resistor, they add up to the applied voltage. And we said when we left off last time that there's a name for that idea, and that's called Kirchhoff's voltage law. And there are two ways of specifying Kirchhoff's voltage law. One is says that the applied voltage is equal to the sum of the resistor voltages. And that's what we have been using up until now. The second form says that if I add up all of the voltages, including the applied voltages, starting to write it. All of those voltages have to add up to 0. Now, so that means the sum of the voltages around a closed loop equals 0. And let's talk about that. A couple of things to, well, let me give you a minute to jot that down first, and then we'll talk about it.
That says loop.
Yes, closed loop. So let's talk about what that means. The sum of the voltages. First thing is we have to add the voltages. It's not the total of all of the voltages without regard to polarity. We have to worry about the polarity. Closed loop means we start and end at the same point. So let's look at the last problem we had and see what we can get from that.
Wait, I'm sorry, I have a question.
Yeah,
So this law only it only applies to series circuits, right? Or
yes.
does it? Okay.
This is only applying, yeah, when we get to parallel, it'll be different.
Okay, thank you.
I just realized I'm in the same one from last class. All right, let me, hold on one second. I want to get into today's sheet. I'm not going to change anything. All right. So let's do a problem and we'll see how this applies. Let's say, for argument's sake, we'll make it a really simple circuit. So if we were going to solve this problem, what's the first thing we do? From last class, we talked about this.
I don't think your screen is showing.
Yeah.
Oh, thank you. There we go. So
Oh.
here's where we were, and we just added this to it. I'll give you a minute to jot down the circuit.
We look for REQ.
Yeah, the first thing we're going to do is we're going to solve for REQ.
Yeah.
So we say that REQ is R1 plus R2 plus R3 plus R4. So I have 3/3.
1K ohms.
So we have 330.
That 1K ohms, right?
Yes, 1K ohms. 330 plus 470 plus 200 plus 1K. And that should come up to be 2K ohms. Now what do I do?
You read
You
that.
A couple of people talking once. What? Say it again.
Wait, is it
um
1K ohm?
Who had? What was the question, Jancy?
Oh no, never mind. I didn't see resistive flow. Never mind.
Okay.
do you take the like the voltage from the source and then like you put that over the combined resistance?
Yeah, because remember what we said we were going to do is we said we're going to take my original circuit. We've reduced the equivalent down to one equivalent, the individuals to one equivalent circuit. So now what we've got is is Vs of 24 volts. That we had the Req of 2K ohms. That this point would be point A, and this point would be ground. All right, all of the other points, B, C, and D, disappear because what we effectively did was we made this, you can think about this as one big super resistor, if you want to call it that, that starts at point A and ends at ground. All right, and I'm going to take that away because it's going to get in the way later on. And now we know that flowing in this circuit, we don't know that yet. Flowing in the circuit is going to be IT, which we're going to find a value for now. So the next thing we can do is from this circuit, actually, we can say that IT is going to be Vs over Req. Vs is the only voltage, Req is the only resistance. Ohm's law says I is equal to V over R. So we know we have 24 volts divided by 2K.
You get 12 milliamps.
12 milliamps. And if I look at this, that's the only thing the only other thing I could solve for in this circuit would be the total power. All right, I could say that the power total is, so remember power, you had a bunch of formulas. I'm going to use V sub S squared over Req. I could have used V is equal to I times R. P is equal to I times V. P equals I times V, 12 milliamps times 24 volts. But why is it preferable to use this formula, Vs over Req? Any ideas? The answer is because this is a given value. This is sort of a given value. Admittedly, if you made a mistake calculating Req, then all of your answers are going to be off. But this is another step away. So worst case scenario, if the numbers weren't as pretty as this, nice and even, you'd have round off error because you had a round off error calculating Req, and then you take that to the next step, use that rounded value to calculate IT. So we could end up with, worsening the round off. This at least is a given value. So I have 24 volts squared divided by 2K. $288 milliwatts. And again, this power calculation isn't necessary unless asked for. Right now, I've got enough to go back up to the top to do the rest of it. So now I've solved for everything I can solve for in this bottom circuit. Now I can go up top, and what do I know about IT? What's the value of IT?
What is IT?
The current through the circuit?
So the current, is T for total?
Yes. I don't really like calling it total, but we're going to call it total because I think that's what the book calls it.
Okay, 12 milliamps.
24.
We've taken this value that we calculated and brought it up to here. Because if this is really equivalent to this whole circuit, well then if 12 milliamps flows out of the battery here, 12 milliamps has to flow out of the battery here, or they wouldn't be equivalent. I can't have a different value of current here and a different value of current here and say that they're the same. They're equivalent. So once I know the current in this circuit at the bottom, I know I can bring that value up. So now I know I've got 12 milliamps flowing through R1, 12 milliamps flowing through R2, 12 mils through R3, 12 mils through R4, and back to the battery. Remember, that's what series circuits, one of the rules of series circuits was, that the current is the same through each element that's in series. So now I know the current in R1 and the resistance of R1, current in R2, resistance of R2, current in R3, resistance of R3. And I can now proceed to solve for VAB is IT R1. So that's 12 milliamps times 330. .96 volts. VBC is IT. Between B and C, we have R2, so we use R2. 12 milliamps times 470. 5.64 volts. By the way, you all have calculators that have storage on them. If you have a number, let's say REQ doesn't work out to be a nice, pretty value like 2000. Let's say it worked out to be 1,984 ohms. Or like when we get to parallel, it's going to be even worse. It's going to be like 4,728.64 ohms. People write them down, and what drives me absolutely crazy is they write them down and then they re-enter them into the calculator. You have memory on your calculators. You could just as easily take that value with all its decimal places and store it in your calculator. And anytime you need it, you can just turn around and say, recall memory, whatever memory you stored it in, and that value comes up with all the decimal places, and you don't have to worry as much about round-off error. Okay, so when I came up with 12 milliamps, not to mention, you've all heard the phrase, necessity is the mother of invention? Yes?
Yeah.
Now is when you say yes or no.
Yeah.
Yeah, you've all heard the necessity is the mother of invention. I add a corollary to that that says laziness is the mother of necessity. People do things because they're lazier and find an easier way to do things. Well, if I store this in, let's say this had 4 decimal places, 12.345. I could enter 12.345 every time I wanted to, EE minus 3 every time I wanted to, or I could just go recall A. Two presses of the calculator, and it pulls the value up with all the decimal places and everything. So it even makes the problem easier. So,
Where are you seeing this recall button?
on the TIs, hold on, I just have to find that.
On the TI, you do store, and then you put it in a variable, like A, B, C, or D, or whatever.
Where store?
The bottom left, it should be somewhere, STO. Or maybe near the enter, I don't remember.
I did download that TI app, and now I can't find it.
It's on top of on the TI-84.
I see that. I'm pressing it and it's just showing me an arrow. Well, right now it's showing me answer and then an arrow. Then what?
All right, wait a minute. Let's get to the calculator later. Let's go through the
If you have it on the computer, if you download it, it's called TI Smart View. If you want to just look for Or just type smart view into that question mark, the search.
Oh, I have an actual calculator.
Oh, is it a TI?
Yeah, 84.
Okay.
I see the store. It just when I press it, it just says and. So like the previous answer that I have, and then it was an arrow.
Okay.
So what do I
so
press?
down here, you've got store, right? Oh, I got to share this. Hold on. Okay. So down here, you have store.
Mm-hmm.
So let's say I have this, let's say I do a calculation and I want to do 25 divided by 8. And I end up with this, oh yeah, hold on. So 25 divided by 7. And I end up with this ugly number over here. And I
Yeah.
don't want to keep typing that in anything. So if I say store and hit, do I have to hit the second function A? No.
Alpha.
Alpha A. There it is. Alpha A. It says it's going to take that answer and store it in memory location A. So when I hit enter, that value is now stored in memory location A. So let's say I wanted to take 63 times this ugly number. What drives me crazy is when people write down this ugly number and then re-enter it into the calculator when they could just do what we just did, store it, and say 63 times second function recall alpha A, enter, and there,
Okay. Okay.
all right, so there's
Actually,
my,
you can actually just type 63A and it's enough.
whoa.
Yeah.
I didn't know that. I don't use the TIs that much because I have some real issues about, anyway.
So I would use 63 and then I would just press alpha and then A so I could get 63A and then that would be that.
Yeah, you can try it now. Just press enter to show the answer and then do it 63A
So if I do 63 alpha A,
and enter.
it comes up with the same answer. That's nice. That only works for multiplication though, right?
No, actually,
It
you
has
can
to.
do 63 to the power of A. It doesn't matter. I mean,
No,
it
no,
will
what
work
I'm
with
saying is you couldn't do it with division.
63 divided by A.
Yeah.
Yeah, you do 63 divided by A.
Right. No, what I'm saying is just entering 63 divided by. So if I do 63 divided by alpha A,
Yep.
enter. Oh, look at that. So you don't even need to do the recall. The recall is sort of automatic.
Yeah. And if you call it instead of A, you call it I, it even makes sense.
Yes, it does. Too bad they don't go up to V. Anyway, all right. So now that we've taken a digression from the calculator a minute, let's go
They
back.
do go up to V.
Say again?
They do go up to V. It goes up to
Oh, it does.
number
Look at that.
the letter Z and then I
Yeah,
see
you have all
Yep,
letters.
Yep,
Yeah.
all the way down. Yeah, okay.
plus data.
Okay. All right. So let's go back to here. So the bottom line after that digression, which is a good digression, but sort of off track for a minute, is what I would do is the minute, because I know, let me back up a minute. I know that I'm going to take this value and I'm going to bring it up here and use it at least 1, 2, 3, 4 more times. So if I store this in memory, like we just showed how to do it, or we just learned how to do it, if I store that in memory, then every time I want to use it in the formula, I just have to do 330A, 470A, 200A, and it will multiply and not have to type in this number. 12 isn't bad, but it's still 12 milli, so it would be second function EE, 3 change sign or -3, depending on the order on that. So anyway, so let's do the rest and get back to Kirchhoff's law. So VCD is going to be IT Between C and D, we have R3. So that's my 12 milliamps again, times 200. So that's 2.4 volts. And then VD, how come there's no second subscript here? What was the rule we said last class? If there's no second subscript, the second subscript is assumed to be
Wrong.
ground. All right. So between D and ground, we have R4. So it would be IT R4. So 12 milliamps times 1K, 12 volts. Now, up until now, what we've done is we've just drawn a line, added them up, and said these, if it's right, all of these add up to 24 volts. That was using Kirchhoff's voltage in the first form. The second form says we're going to add the values all the way around the circuit, closed loop, and they should add up to 0. Now, to make sure we do that right, what we're going to do is label each one of the resistors with its associated voltage. So this voltage is 3.96 volts. And we said, anybody remember our polarity? The end that the current goes into is the plus end or the minus end?
Plus.
Plus end, right. And current comes out of, well, let me put the next one up, 5.64 volts. Current comes out of the 330 ohm, goes into the left-hand end of R2. So that's the plus end. Leaves the other end, that's the minus end. Next one is 2.4 volts. Current goes into the top, so that's the plus end. Leaves the bottom, so it's the minus end. Comes out of the, well, let's put the next one in first. This is 12 volts. Leaves the bottom of R3, goes into the right-hand end of R4, so that becomes the plus end, and the minus is on the left. Any questions on how we put the voltages we calculated into the diagram, or how we got the polarities that we associate with the voltages? Okay, so
Wait, I'm sorry. I was on a phone. Someone called me. How do you get the polarity again? Is it just from the symbol from the battery?
no. Well,
Okay.
yes and no. The symbol from the battery is going to tell us where the current goes. Current always leaves the positive of the battery, goes through the circuit, and returns back to the negative.
Okay.
So once we know that the current in this case is going clockwise through the circuit, the individual resistor voltages,
Right.
the end that the current goes into is the plus, the end it leaves is the minus.
Right. Okay. Thank you.
Okay. All right. So let me talk about, so Kirchhoff's voltage, the second form, says that the sum of the voltages around the loop is equal to 0. And since we're using it here as a test, we can put that as a question mark. So let's do that. The sum of the voltages. Now, closed loop means we start and end at the same point. I'm going to start at A. Nothing that says I couldn't have started at B or at C or at D. But if I started, let's say at C, I want to start at C and add this voltage, this voltage, this voltage, this voltage, this voltage to get back to C. But I'm going to start at A and go around. I usually like to start at the positive of the battery. So if I do that, I'm going to have VAB. Well, let me just do it in numbers to start out. I'm going to go here, and I hit the end that you hit is the polarity you're going to use. So if I'm going clockwise around the loop, I hit the left-hand end of A first. So I'm going to write that as plus 3.96 volts. Plus, then I get to here, Going clockwise, I hit the positive end of the voltage across R2. So that's going to be plus 5.64 volts. Plus, we hit the top end of C going clockwise, plus 2.40 volts. Plus, we hit the right hand or more positive end of R4 first. So that's 12 volts. Plus, now when I get to here, I hit the minus side of the 24 volts first. So we're going to add to that negative 24 volts. That should add up to 0 volts. Okay? So again, remember, if you don't remember, the long bar is the plus bar. The short bar is the minus bar. So I hit the negative side of the battery first. So we're adding a negative 24 volts. We remember, summing is addition. So we add this plus this plus this plus this plus this. This happens to be a negative value. So we're just adding negative 24. Somebody with a calculator want to check that out and see whether it's 24 or not?
Yeah, it's good.
So just to double check, that's like sigma volt and then equals 0.
Yeah, sum of the voltages equals 0. So if I go around a closed loop, okay, making sure I start and end at the same point, I should come up to 0 volts.
So they basically developed this as a way to make sure and check that your math is correct.
Well, no.
Oh.
I'm gonna give you a problem in a minute. I'm gonna give you one practice problem first in general, and then I'm gonna give you a problem where maybe it might look like this. Okay. So maybe you know this voltage and you know this voltage and you know this voltage, you know the 24, but you don't know what the voltage is over here. Well, if I know this and this,
you would have the difference.
this is the missing one. So this would be question mark. I could just go around and say this plus the unknown plus this minus the battery have to equal 0. So I could solve for that one. Okay.
Okay.
But for right now, we are going to use it as a check.
Just the very last question is like, so are we supposed to be going clockwise, or are we supposed to be going like will there ever be an instance when we're going counterclockwise? Like, will a problem tell us to go counterclockwise?
Absolutely. Well, the answer to your question is, do we have to go clockwise? And the answer is absolutely not. Matter of fact, what I'd like you to do, and we'll come back and answer your second one first, is to prove two things. Number one, that you don't have to start at point A. So what I'd like you to do is, starting at point C, go counterclockwise through the circuit, add up the voltages, and still see if they still add up to 0. So try that. Going counterclockwise, starting at point C, add up the voltages, and see if they come out to 0.
So,
let's take a look at it and see how you made out. If I start at point C and go counterclockwise, I first hit this resistor, and I hit the negative sign first. So this is going to be minus 5.64 volts. Then I get to this resistor, minus, and it's 3.96. So actually we should put this as this plus a minus 3.96. Now I come over to here and I hit the positive side of the battery first. So it's plus 24 volts. Plus, now I get to here and I hit the minus side of the R4 voltage. So it's minus 12 volts. Then I come around and I get to the R3 voltage, and it's the minus sign first. So we're adding a negative 2.4 volts. And that takes me back to C. So the question is, when I add all of this, negative 5.64 plus 3.9 plus a negative 3.96 plus positive 24 plus negative 12 plus negative 2.4, do I still end up with 0?
Yeah.
Yeah, you do. So the bottom line here is that I could go clockwise around the circuit. I could go counterclockwise around the circuit. I could start anywhere I want in the circuit. The only thing you have to make sure is that you start and end at the same point.
Okay.
Okay, so now getting back to the second part of your question. Are there times when you want to go clockwise versus counterclockwise? We'll see later on when we do nodal analysis or mesh analysis. Sometimes we might want to have this voltage turn out to be a different value. Or sometimes when we do a nodal or a mesh analysis, we'll be told you always want to go clockwise or you always want to go counterclockwise because there'll be multiple parts of a circuit. So the answer is a categorical, it depends on what you're doing. For a circuit like this, all right, I could just as easily go clockwise or counterclockwise.
Okay.
Okay?
Yes, sir.
Okay. So here's, there it is. What I'd like you to do is take a couple of minutes and see if you can solve for the REQ, the IT, voltage from A to B, B to C, C to D, D to E, D, F. All right, let's take a look at it before we run out of time. So what we're going to do is we're going to solve the problem. We're going to start out by finding RT, or REQ rather. And REQ is going to be R1 plus R2 plus R3 plus R4 plus R5 plus R6 plus R7. So we've got 470 plus 8.2K plus 1.1K plus 330 plus 2.7K plus 560 plus 240 . $13,600 ohms.
REQ equals 13.6, you're saying? Yeah. Wait, what?
Yeah, 13.6.
Yeah.
13,600 ohms or 13.6K.
Yeah.
So we're going to redraw our circuit. Remember, this is point A, and this is going to be ground. Now we have a lot of values to solve for, so I'm going to just put the current down here. Normally I would put the current over here, but I want to leave myself enough room to make sure that I can solve for all of the voltages. So I'm going to say that the IT Actually, let me. IT is VS over REQ. So it's 15 volts divided by 13.6 K. Uh, 1.1029412 milliamps.
How many decimal points do you want? I only did 3.
All right, so my rule of thumb for general things, I mentioned this before. When you do the calculation on your calculator, you end up with, so if I do this, let me share this very quickly. So if I do 15 divided by 13,600, 15 divided by 13,600, I end up with 1.102941176 to the minus third, or 1.0 milliamps. This is a really nice number. It's a really ugly number. One of the things I did with this right off the bat was I did a store alpha I.
Yeah.
So I stored that. So I'm going to do my calculations to that many decimal places. However, writing it down, and my rough rule of thumb is, let me go back to here, is to work to 4 significant figures, not decimal places, but 4 significant figures. So I've got 1, 2, 3, 4. So my 1.1029 became 1.103, and round my final answer to 3, because I'm not going to be able to read to more than 3 significant figures on an instrument anyway. So why am I going to, write down 9 decimal places or 9 significant figures if I can only read an instrument to 3 significant figures? Okay.
Gotcha.
But
I think you told us that before,
I
like
did.
solve for 4 round to 3.
Yeah.
I forgot.
So what I'm going to do is, even though I'm going to write my answers to 3, what I did was I stored that current value with all of the decimal places that we saw before, the 1.1029,
Yeah.
all of that. That's the number I'm going to do a recall for and use when I multiply.
Yeah, I did the same.
Okay, so VAB is going to be IT times R1, because R1 is between A and B. So I've got the 1.103 milliamps times 470. And that worked out to,
I got like 518.4 milliamps roughly, something like that.
um, 0.5184.
Yeah, I ended up getting it as milliamps, but then I converted it when I had to add it all together to make sure that the voltage was total. So yeah, 518.
And it's, remember, this is a voltage, so it's in volts. Okay. So if I take this and with all the decimal places multiply it, this is what I get. Okay. VBC is IT R2 1.103 milliamps times 8.2K. So when I do that, $9.044.
Yeah. I just,
By the way, what I also did was, because I knew we were going to be putting all of these up, what I did was I did a store of the voltage value, this value. I did that in store alpha 1, which is really Y, but I figured 1 is R1. So even if it comes out Y, as long as I do alpha 1, the 1 key, I'll know that that's 1. And I did this as store alpha 2, which is really Z. All right. And I'm not going to do this. These would all be the same because we're getting close on time. And I want to do one other thing. So VCD, VDE, VEF, VFG, and VG. So, 3. $1.213 volts. This is going to be 0.3640. This is going to be 2.978 volts. Zero point 61776 volts.
I thought we were only rounding to like the first 3 and not
Or, you know, it would have been
matter.
yeah, this would have been, so you can take this off. This would have been, I wrote them to 4, but we would have normally done them to 3.
Okay. No worries.
0.265 if I go to 3. All right, so those are the values you should have gotten.
Yeah.
And
About
I'll
that.
leave you to, if you didn't get them, to go through and figure out. They were all current times the resistance, current times the resistance, current times the resistance. Okay. So we could use Kirchhoff's voltage law to check it. And yeah, looking at the clock, we're not going to get to what I wanted to anyway, so let's do that. So if I do 0.5184 plus minus 9.044 plus minus, these are all in volts. I'm just trying to save some. 1.1 is 1.213 volts, plus at the top, minus at the bottom, 0.3640, plus on the left, minus on the right, 2.978 volts, plus at the top, minus at the bottom, 0.6176 volts, plus on the right, minus on the left, and 0.978 .265 volts, plus on the right, minus on the left. Questions up to here on how we got any of that or why the polarities are the way they are?
No, sir. But sorry, just the only question that I kind of had is that when I was doing it through the calculator, it was automatically giving me milliamps. I just ended up converting it anyway. But did you end up getting it? I'm sorry, millivolts. And I converted it to like regular volts anyway. Is that what we're supposed to do, or are you doing something on the calculator that's automatic?
No, mine just came up in regular volts. So, oh, actually, I don't remember how they came up, where they came up in volts. All of these values I pulled out of storage. So I don't know whether that changed. I didn't really look at, I was just grinding through the problem. So I don't know whether or not it gave it to me in millivolts. I know the current came up in millivolts when I did that calculation. Let me do this. Second, let me clear this first. Second, yeah. When I did the calculation, it came up as 1.1029412 E minus 3. I stored it. When I came back out of storage, it came up as 0.0011029.412. So when you store it, it must go back to base units and not metric prefixes. I don't know why that is, but anyway. So this, yeah, this would have been, if you wanted it 265 millivolts, this would have been 617.6 millivolts. This would have been just volts. This would have been 364.0 millivolts, and so on.
Yeah. Okay, I gotcha. Thank you. I was just wondering why, but I mean, I
No,
could.
it looks like the calculator, when you store it, brings it back up in base units.
Okay.
I haven't looked at whether or not, if I put this into engineering mode. Yeah, maybe that'll do it. I'll have to see. All right, we're just about out of time. I had wanted to go through one of those problems that I had mentioned before where you might not have a value. And that's where we'll start off with next class. What we'll do is, very quickly to show you what we're going to end up with, is what if I do if I have a problem like or I gave you something like this, even better. And I asked you to solve for all the voltages and currents. So that's where we're going to take off next class. Next class we'll be actually starting with this. So this would be A, B, C, D, ground. All right?
Okay. Thank you.
All right. Have fun in Professor Atwood's class this afternoon. You guys have him for 110 this afternoon?
Yeah.
All right. have fun in that class and see you on Thursday.
All right, thank you. See you Thursday.
Take care.
Thank you. Have a good one, Professor.
Actually, would any of you guys be able to let Professor Atwood know that I have a doctor's appointment? Like, I'm gonna send him an email, but if he asks.